Hi everyone, this is my video lab report for Physics 2212 Lab 3 circuits. The purpose of this lab is to use the loop and node rules to predict the behavior of circuits with resistors in series and parallel, along with using multimeters to measure true values of conventional current and potential differences in the circuit, and examining the behavior of ohmic resistors and capacitors. The materials used in this experiment include two 1.5-volt batteries to supply 3 volts of potential difference total, wires, two resistors of 47 and 100 ohms respectively, a 1 farad capacitor, two light bulbs of 2 ohms and 4 ohms respectively, and a multimeter. The fundamental principles in this lab include the node rule, which states that the current into a node must equal the current out of a node, the loop rule, which states that the change in potential difference across a circuit is zero, and Ohm's law, which states that the potential difference is the product of conventional current and resistance. Lastly, the system is the circuit while everything else is in the surroundings. In the first experiment, we were tasked with implementing a circuit consisting of two batteries, two ammeters, and two resistors of varying resistance in series. We swapped the two resistors in our implementation, but this wouldn't affect any outcomes. In this part of the experiment, we measured the current through both ammeters, which was 19.7 milliamps and 19.4 milliamps respectively. The discrepancy might have been due to sources of error which will be described later, but generally the circuit followed the node rule in that the current through each node in the circuit remains constant. The next step was to calculate the potential differences across different parts of the circuit, including the batteries and resistors. Across the batteries, the potential difference was calculated to be 2.9 volts, while the voltage at the 100 ohm resistor was 1.8 volts. Lastly, the voltage at the 47 ohm resistor was 0.8 volts, and these values will be used to calculate the total potential difference of the circuit. The potential differences found on the last slide are calculated here. Because V is equal to E dot delta length, each potential difference is negative. And since the field inside the battery points opposite to the rest of the circuit, its potential difference is of the opposite sign. The experimental potential difference across the circuit was calculated at 0.2 volts, which is close to zero and can be attributed to error. Because V is equal to current times resistance, the largest resistor has more potential difference than the smaller one, hence the steeper gradient in the graph. Ultimately, this circuit follows the node rule and loop rule. The last part of experiment 1 was to connect an ammeter in parallel to the 100 ohm resistor rather than in series, as shown in the diagram. This caused the current to spike through the ammeter, as the current now had two potential paths to flow through, and it chose the path of least resistance, which was through the ammeter. The node rule is still conserved, as there is very little current flowing through the resistor in the setup. In the second experiment, two light bulbs of varying resistance were attached in series with two 1.5-volt batteries and a 1 farad capacitor. When the circuit is first complete, there is no voltage in the capacitor, so the bulb shines brightly as if there were no capacitor. However, as the capacitor charges, its voltage equals the voltage supplied by the battery, thus reducing the current to the bulb and causing it to dim. The time it takes for the bulb to dim is the charging time. Next, the battery is disconnected from the circuit, and the capacitor is the only object connected in series with the light bulb. This causes the light bulb to illuminate at first, since the capacitor is charged, but as the capacitor discharges, the bulb dims, and that time is the discharge time. The more resistance in the circuit, the longer it takes to charge and discharge due to the reduced current caused by greater resistance. The loop rule still applies here in this experiment. Because this lab was purely experimental, there weren't any assumptions made when collecting the data. However, there were several potential sources of error. This includes errors in the multimeter reading, which likely contributed to the discrepancy in the potential difference calculations earlier. Also, the materials in this experiment were imperfect, which contributed to slightly erroneous readings. Lastly, human handling of the circuit, along with stopwatch error, could have contributed to the error in this experiment. What if we charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Is this realistic? To begin, resistance limits the flow of conventional current, so removing that would make the capacitor charge up almost instantly. However, this isn't exactly realistic since each component of a circuit has some resistance in it, so while it will be fast, it won't be instantaneous. Thank you very much for watching this lab report.